Alrighty, so welcome to our 6th rep lecture on digital filters and synchronization. So let's see what we're going to talk about today. So first is the digital filter section. So previously we've worked on analog filters, and digital filters are similar, yet the fact that you're working in a discrete time domain kind of mixes things up a little. And also the fact that you have to work with finite memory. So we'll talk about that. And then synchronization, the problem here is that your transmitter has a different time base than your receiver. And so you need some way of synchronizing those two things in order to effectively communicate. So first, the digital filters. So previously, last lecture that is, we talked about how to demodulate quadrature modulation. And in that process, there's filtering you need to do. So specifically, kind of highlighted in red there, I hope you see it, is we need to do a low-pass filter to obtain the in-phase and quadrature components of the modulation. And without that filtering, we have this double frequency component that we can't get rid of very easily. So in the assignment 5, I believe, you guys used a MATLAB function to do the low-pass filtering. And the problem with using MATLAB functions is, A, you don't really know how they work, and B, you don't have MATLAB functions on something like a microcontroller, so you'd have to actually implement it yourself. So we got to figure out how to implement them. So this particular instance of filtering is just one tiny subset of all the digital filters that go on all the time. So for example, with audio processing, there's equalization is just one example of many. So, you would might attenuate higher frequencies and amplify, or I shouldn't say amplify, but attenuate less lower frequencies if you want to improve the bass in audio clip or something. In image processing, there's tons of applications. There's blurring, there's sharpening, there's edge detection, and so on. And all of those are forms of filters, digital filters specifically. There's servo control, so that's all of that feedback control system stuff you learned in 141. So there's motor control. So PID control is an example of a type of filter, though it's not usually called a filter. There's temperature control, and there's things that don't actually involve physical moving objects or kinetic energy with temperature, but and then those occur in circuits and other things, and so it's a very common topic, and so the list goes on. So for those who haven't taken 113, I just want to make a quick note on notation. So when we write x of t with the parentheses, what I'm implying is that t is in the set of all real numbers, so t is continuous. And then when I use x of n, where the n is in brackets, I'm implying that n is a discrete number, so it's in the set of integers. And that refers to a discrete time signal. And so the n is basically representing one particular point in time, and that's how we represent discrete time signals. Also, when I write a delta function with those brackets, I'm not using the Dirac delta function, where the problem with the Dirac delta, the value at 0 is not well defined. But with the Kronecker delta, which is what's used in discrete time signals, the value at 0 is 1, not 0. And it's 0 everywhere else. So the sum of the delta over all time is still 1, but the value at 0 is actually defined. So that's just some notation. And also, I want to mention an important property of the Fourier transform that hopefully you pick up at some point, because it's like one of the most important things to know. I shouldn't say the most important thing, but one of them. So if you have a signal in the time domain that has a very short duration, what that means inside the frequency domain is that the bandwidth of that signal is very large. So in the extreme case, here I have, let me get out the pointer thing. Here's the pointer thing. So in the extreme case, I have y1 here is equal to a delta function, and the Fourier transform of that is just 1. And maybe if you're used to a different form of the Fourier transform, there'd be a normalization constant there, but this is the one I'm using. And of course, by duality, we have, if we have a function y2, which equals 1, the Fourier transform is the delta function. So what this is showing is that if we have a signal that is, infinitely short in time, right, the delta function, the bandwidth of that signal is infinite. So in this case, the constant 1 is infinite bandwidth. And then vice versa, if we have a signal that is infinite in time, the bandwidth is infinitely small. And I also want to point out that if you have a sharp transition in a time domain signal, that's also going to result in a larger bandwidth in the frequency domain, and also vice versa by duality. So here I have y3, which is a rect function. So let me draw this out quickly. So here, I have a standard rect function. So that'd be y2, and then in the frequency domain, I'd have some sinc function, right? And I added the scaling factor here, a, so at. And so as I increase a, I'm making the rect pulse shorter. And in doing so, I'm making the sinc wider. So the same thing we had with the delta function, we have with the rectangular and the sinc function. Shorter duration means larger bandwidth, and larger bandwidth means shorter duration. So that's that. Any questions so far? Okay. So now we get into the actual filters. So first is the infinite impulse response filter. And I write here, as the name suggests, the infinite impulse response filter has an impulse response that lasts for an infinite amount of time. And so this is the type of filter that you'd see in basically any analog filter. There's some exceptions, but like down here, I'm showing the generic low-pass RC filter, and it has this impulse response if you work out through the math, where the U of t is the Heaviside step function. And if you draw that out, of course, that's going to look something like this, right? And so it has an exponential decay. And we know that an exponential decay, although it approaches 0 as t goes to infinity, it never actually reaches 0. So that means that the impulse response lasts for an infinite amount of time. Although, for a time t less than 0, it's 0, but t greater than 0, it's non-zero. And in the frequency domain, that just results in a single pole filter, and nothing too special there. But the key point here is that the fact that the impulse response lasts for an infinite amount of time, that means that if you were to implement this in the digital domain in a naive manner, your computer system or your digital system, we need to have an infinite amount of memory in order to keep track of all past inputs, because you have to convolve your infinite impulse response with all past inputs in order to get an output. So in practice, like the low-pass filter here, the impulse response usually goes to 0 after some period of time. And for this guy, we could say it goes to 0 after 5 to 10 time constants, so RC seconds. But still, that presents a problem with implementing it in the digital domain. Okay. So how do we actually implement this in the digital domain? We use the concept of feedback. And if you've taken 141, you will know more about this, but if not, don't worry. So the idea is that by using a feedback network, in addition to a feed-forward network, which is this filter A, you can implement a infinite impulse response filter while using a finite amount of memory, which is a big advantage, right? You don't want to use an infinite amount of memory. So as a quick example, this is kind of similar to the RC low-pass filter. Here I have the discrete impulse response, here h of n, is equal to a to the power of n times u of n, where again, u is the Heaviside step function. And so assuming a is between 0 and 1, this is just an exponentially decaying function, right? So nothing too special there. And if I take the z transform instead of the Laplace or Fourier transform, I get this, which is, very, very similar, single pole system. If you haven't taken 113, you may not know what the z transform is. It's basically the discrete form of the Laplace transform, but don't need to really worry about that too much, just for your information. And so if you were to implement this in a digital system, you can turn it into a feedback system, feedback filter. So here I have y of n is equal to x of n plus some constant a times the previous y of n, so y of n minus 1. And so this term here is the feedback, essentially, because we're using previous outputs to affect the current input. Okay, any questions on that? Okay. So there's always pros and cons to these different types of filters, because otherwise we'd only use one type of filter if they only had pros. So in the case of infinite impulse response filters, the good thing about them is the fact that they have infinite duration, they can achieve an infinite duration in time, means that they can have very sharp transitions in frequency, which is like what I said before with the rectangular function and the sinc function. The rectangular function has very sharp transitions, and the sinc function has an infinite duration in time. We have a previous question on the previous slide. Is x the input? Yes. I should have written that here. So x is the input and y is the output. Okay. And then so here, this filter B would be a z to the minus 1 times a, which would represent, the z to the minus 1 just represents a delay of 1. And the a means you're just multiplying by the constant a. And we add that back to the input here. So this creates this term here. Okay. So yeah, so by using a infinite impulse response, you can get high or sharp transitions in frequency. And what that means is that, say you have a low-pass filter, for example. So here's frequency. You could have a very sharp transition, as opposed to if you had a finite impulse response, you might have something more gradual. And having very sharp transitions can be helpful if you have, like your signal of interest is right here, and the thing you're trying to filter out is right here. And clearly, this more gradual filter won't do the trick in getting rid of that second interference. So the disadvantage of these IIR filters is the fact that you have to implement them with feedback can cause instability. Well, not just the feedback, but the fact that they have an infinite impulse response can lead to instability. So, for example, if you have 0 input to your filter, you could start having an output, which is not desirable, right? It would basically be an oscillator, or even worse than an oscillator is just, let's say you had exponential rise in your output without any input, that would just be an unstable system. So that's no good. And partly because of that, but also due to all the feedback stuff you have to worry about, they're a little more difficult to design than the FIR filter, which is what we'll talk about right now, unless there's any questions. Okay. So next is the finite impulse response filter, or the FIR filter, which it's a very, very common filter for digital systems. But finite impulse response means the impulse response goes to zero, and exactly zero, after some finite amount of time. So we had the exponential decay before, that doesn't quite go to zero. So finite impulse response filter will have a actual cutoff point where after which it goes to zero. So here is zero. So that is the difference between them. Okay. And the fact that they have a finite duration in time means that the sharpness of transitions in the frequency domain can't be as sharp as a similar order infinite impulse response filter. So you can still achieve sharp transitions if you increase the complexity of the filter. I write here that you don't really see them in the analog domain, mainly because in the analog domain you have those exponential decays and everything, which are infinite, but you do see them in the digital domain. So because these are the ones we're actually going to be using, I want to point out the math here. So this is the generic impulse response for a FIR filter. And so all that this is saying is that the impulse response is just a constant at one position plus a constant at another position shifted by one, and so on until you get to the length of your filter n. So this might look something like you have something at 0, and then you have something at position 1. You might have something at position 2, 3, 4, and then 5. And then after that, let's say, it goes to 0. So after that, no more impulse response. It's all 0. Right? And again, we're using the Kronecker delta here, so that's why these aren't little infinite spikes. So this would be the H, and this would be N. Okay, and then the actual output, you can write directly as a function of the inputs. So if you convolve H of N with X of N, you clearly just, you have a bunch of deltas here. So you have a bunch of shifted X's of N's multiplied by constants. So you'd have just be 0 times X of N plus B1 times X of N minus 1, and so on. And the good thing about this is that you only need to store the past n minus 1 inputs as well as the current input. So a total, actually I think this should be, sorry, this should just be n, past n inputs as well as the current input, as well of course as the BIs, the filter coefficients. And so you'll often see the filter coefficients called taps. So you might have an n-tap filter, for example, which just means you have n coefficients. That's just terminology. Okay, so an example of an FIR filter is just the simple moving average. So what we're doing is, say we have an input stream of X of N, and that might look like a point here, point here, point here, point there, and so on. Then you want to take, say you're right here in time, you want to take the past 3 inputs, take these guys, average them, and that's your current output. So here n is equal to 2 because we're taking the previous 2 inputs plus the current input, so 3 total. And clearly the output could just be rotated straight, like 1/3 of x of n plus 1/3 x n minus 1 plus 1/3 x n minus 2. And if we want to write that more generically, we'd write the BIs as 1 over n plus 1. So here n is 2, so you get 1 over 3. And likewise, we could write the impulse response as just shifted delta functions multiplied by 1/3. And if you went through the math, you'd find that the z transform of this impulse response is 1/3 plus 1/3 of z to the minus 1 and 1 plus 1/3 z to the minus 2. And again, the z to the minus 1 just means a delay by 1, and z to the minus 2 means delay by 2. And then if you look at the frequency response of this guy, you can kind of ignore this stuff. That's just negative frequency. But if you start here, you see it has a low pass kind of shape. And then at some point it goes to exactly 0 and it starts rising back up. That's kind of a property of digital-ish filters. Also, if you look at the phase is linear, which is an interesting property because if you recall from the analog filters we looked at, the phase is not always linear. And there's some implications that has for communication systems, namely, if you have a nonlinear phase, you have what's called a non-zero group delay, or I should say, non-uniform group delay. And what that does is it can distort your signal by shifting the phase of some frequency more than others, and usually you don't want that. So that's the good thing about FIR filters is that they have a linear phase. Okay, so as I said before, linear phase. Also, they're pretty simple to design compared to the IIR filter. There's no feedback, no nothing. You just have a set of filter taps, and you just multiply them by the past n inputs and the current input, and you're off to the races. Because they have a finite impulse response, FIR filters are also always stable. So that's a nice desirable property. If you have 0 input, you're guaranteed to have 0 output. Unfortunately, though, you need a higher order filter to achieve the same roll-off as an IIR filter, because exactly what I talked about, because you have a finite duration in time, you have less steep transitions in frequency. And then the other thing is because you need a higher order filter to get a similar roll-off, the higher order filters tend to have larger delays, meaning you feed in an input and after some delay you start getting an output, and that delay will be larger with larger order filters, and thus it becomes more of a problem with FIR filters. Okay, any questions?
Is Frankie good?
Yeah, Frankie is, he's being fed. Okay, so next we get on to how do we actually design FIR filters. Well, if you hopefully remember the strategy for analog filters, we typically use a known filter shape, like the Chebyshev or Butterworth filter, and we determine what our L's and C's should be based on that filter shape. So one particular way of designing an FIR filter is to take one of those analog filters and then discretize it into an IIR filter first. And you could do that by taking the impulse response, for example, and just chopping it up into discrete time points. But there's a bunch of different methods. And then you could just truncate the IIR filter after some point, and that's called windowing. So you might use a rectangular window, and that would just chop off everything after a certain point. And that would turn the IIR filter into an FIR filter. And of course, chopping an impulse response off does have implications, but if you're careful and do things intelligently, then you can kind of minimize that that effect. And so of course there's programs that'll design it for you. So here I have linked an MATLAB function FIR1, there's also FIR2. And there's also a lot of online calculators that'll tell you exactly what your filter coefficients should be for given stop band rejection and pass band response. So sometimes you don't want any ripple in your pass band like Butterworth filter. Sometimes you do with the Chebyshev filter and so on. Okay. So last time we talked about root raised cosine filters, and those were used in to mitigate intersymbol interference in a communication system. But we never actually implemented that in our assignment. And the reason is because I was kind of waiting till this lecture. So here I have written the impulse response of the root raised cosine filter. And it's a bunch of stuff. You can just look it up on Wikipedia if you want. I copied it straight off Wikipedia. But the actual construction is not too important. What I want to get across though is that you can take this impulse response, which actually looks something like this. It kind of looks like a sinc function, but not quite. It's a little different. And you could turn it into a discrete time filter by just sampling this guy at certain points along the impulse response, and so on. You get the point. And then you could turn it into an FIR filter. These guys continue on for infinity, right? You can turn it into an FIR filter by just chopping off the tails and just considering this part here as your filter. And so that would be an example of using a rectangular window as your windowing operation. And depending on how many sample points you have, you'll have so many taps in your filter. The more taps you have, the more processing you need. However, the better approximation you'll get to the actual filter. And so it's a trade-off between how exact you want your filter to be versus how much processing and memory you want to allocate to the filter. The other thing is, as I wrote it here, if this is t equals 0 in the center, this is a non-causal filter, meaning the impulse response before time equals 0 is non-zero. And those are impossible to create in the analog domain. They are possible in the digital domain. But usually what you'll do is you'll shift this entire filter response to the right so that your new origin, instead of being here, is now over here. And that basically introduces delay into your filter, but you can correct for that. And you'll kind of have to deal with this in your assignment, but I'll write about it. So any questions? Okay. All right, so kind of wanted to give an example of what this looks like. So, so what I did here is I took the root raised cosine. So I literally took this impulse response, I stuck it into MATLAB, and I sampled it at some number of points. So in this case on the right here, this is a total of 10,000 points. And you can see at the center, you get the actual filter response. And at some point, it basically dies down to 0, but not exactly 0 because it's an infinite impulse response filter. And then I zoomed this down to this guy. And so that's what the center looks like. And you can see exactly what I wrote here. You got this sync looking thing. And at some point starts dying away to 0. And so clearly, we're wasting a lot of filter taps because all of this stuff here is basically 0. And that's just unnecessary memory and processing that we need to do if we use all of those filter taps. So instead what we can do is we can chop it off at some point, and that's what this is right here. This is the entire filter from 0 to 100 taps. And at the center, we have the important bit, and you can see it, fairly quickly dies down to 0, and we don't really care what happens after that, because it's an approximation, but it doesn't really affect your output too much. Okay, so any questions about that? Okay, so we can see how that actually looks like in the frequency domain. So if you take the FFT of both of these impulse responses, you get these guys. So the guy on the left is the better approximation, and as you'd expect from a root raised cosine, the frequency response decidedly goes to 0 at some point, which is right here, and after which it's 0 for all frequency. And then if I truncate the frequency response, so that's this guy here. Sorry, if I truncate the impulse response and I take the FFT, they look pretty similar, but you see there's some ripply bits at the top there. The transition from non-zero to 0 is a tiny bit different, but overall it looks pretty much the same. So if you're okay with your filter response looking like this, then it's perfectly acceptable to truncate your root raised cosine filter. And in practice, this will work pretty well. Okay, so next we're going to start talking about synchronization. So if anybody has any questions on filters, please ask it now.
Is there a way to quantify how much worse it gets as you truncate it? And is there some limit that you should watch out for?
So personally, I don't know of a way, though I'm sure there is a way. What I've just done is just do it experimentally. So I'll take a signal, I'll feed it through my FIR filter. And if it looks like what it should look like, it's good. But if I truncate it more and it starts screwing up, that's no good.
Right.
So yeah, I don't know of a way of doing it analytically, but that doesn't preclude the existence of such a way.
I mean, it's probably easier to just do experimentally. I was just wondering if, how you did it, I guess.
Right. Yeah, that's a good question. Okay. Anyone else? Okay. So on to synchronization. So this is kind of an interesting topic. It's less mathy, and it's more, I guess you could say algorithmic, but it's still pretty interesting. So in general, we have a transmitter and receiver, right, in a communication system. And the transmitter has its clock, it has some oscillator that's generating a sine wave or a square wave, and that clock controls the carrier frequency, controls when we send each symbol. It also has its own phase. And so the receiver has its own clock, and those clock frequencies might be different. The clock phases might be different. And so in general, the receiver doesn't know the carrier frequency exactly, doesn't know the phase, doesn't know the timing of symbols. And so that'll present a huge problem when you want to actually detect symbols on the receiver. So I have this nice example here on the right. So remember, this is showing the constellation diagram of a BPSK transmission. And you'd look at it and say, that doesn't look anything like BPSK. And you'd be right, because the receiver doesn't know this information right here. So ideally, you'd have a cloud of points around here. You'd have a cloud of points around here, and you'd easily be able to detect which symbol is which. Here, what I did is, I have a carrier frequency of 100 hertz. It's pretty small, but go with it. The receiver has a carrier frequency of 101 hertz, and the receiver has a phase offset with respect to the transmitter of minus 45 degrees. And there's also some noise, but can't do much about that. That's just, that's not what's causing this weird pattern here. So what is causing this weird pattern is a combination of the phase offset and the frequency offset. So a way to, the phase offset is pretty easy to think about. It'll just rotate these red dots here by some amount of degrees. And after rotating once, they're not going to move. But the frequency offset, you can kind of think about it as a variable phase offset. So if you look at a cosine, for example, you have your 2 pi FCT plus a 2 pi delta FCT plus your phase offset. I'll use theta, okay. Fine, we'll use theta. So we have a theta naught. Right, so that would be the receiver cosine and written in terms of like the transmitter cosine, right? Because you have the delta FC and you have the phase offset. So the phase offset, that's just a constant phase offset. But you can think of the frequency offset, this term here, as a phase offset that's increasing with time, right? Because you have a constant term, this guy right here, multiplied by t, and t is increasing with time, of course. So this entire term is just increasing as time increases. And the effect that that has in the constellation diagram is that the constellation diagram will just keep rotating over time. And so you might receive one symbol and it'll appear here, and the next symbol will appear here, and so on until you get something that looks like this, where your symbols start turning into a circle instead of two discrete points. So that's no bueno. Okay, so we know what the problem is. How do we solve it? So recall what we receive is something that looks like this, right? We have our in-phase term, and this is quadrature modulation, general quadrature modulation. You have your quadrature term, and they're both multiplied by a cosine and a sine respectively, one with a, both with a phase offset. So we don't know theta naught, the phase offset. We don't really know FC, though we have a general idea of what it is, but not down to the hertz or sub-hertz level. So what can we do? Well, we can try squaring y of t. And if we do that, we get this mess here. Well, this entire thing. But if you look at this mess, we can really simplify it in the case of BPSK. So with BPSK, we know that the in-phase term is plus or minus 1. The quadrature term is just 0. And so if you plug those in, you get this guy right here, which is a lot more simple, right? You just have a cosine squared. And if you use your trig identities, you have 1/2 plus 1/2 of cosine times double the frequency. And of course, you have double the phase as well. Okay, so we basically have a DC component, which is the 1/2, and a double frequency component, which is the other guy. And if we were to f of t this entire thing, what would we get? We'd get the DC component, right? We have the double the frequency component, and we could easily detect the double frequency component because it's just a delta at that frequency. So we could exactly know what the double frequency is, and if we just divide that by 2, we get the actual carrier frequency, right? And of course, doing this, I made the assumption that we're using BPSK, but for other modulations, there's more complicated things you could do. For example, you could raise y to the power of 4 instead, and that'll get you the same thing with, like I think 4 quam will do it as an example. So any questions about that? Okay. So of course I have a nice example for you. So where'd my, oh, here it is. Okay. So this guy on the left here is the FFT of just some random symbols I was simulated in MATLAB. And the frequency spectrum is kind of what you'd expect, right? So you have a peak here, which is centered at the carrier frequency. But because we're modulating the carrier frequency, the nice delta function you get is spread out over a range of frequencies. And that has some sort of envelope that decays with as you get farther away from the carrier frequency. But because there's no single peak there, it's very difficult to determine what the carrier frequency is from just this. So if we square it first and then take the Fourier transform, or the FFT, things become very different. So we have the DC term here, and we don't really care about that. But more importantly, we have the double frequency component right here. And now it is a delta function, essentially. Not quite, because this is discrete time, and we're using a finite duration for the Fourier transform. So it's more like a sinc function than a delta function, but it's a very thin sinc function. But it happens to be a double the frequency, and we can easily detect that peak, divide the frequency by 2, and sure enough, we get 100 hertz, which in this case is the carrier frequency. So what does that look like? Well, if we correct for the carrier frequency, we turn this mess of a constellation diagram into something that just has a phase offset. So we kind of collect like points and move them to where they should be, except for the phase offset, of course. Right, and so that's, of course, where we're going next, the phase offset. How do we correct for that? Right, so any questions up till now?
How does squaring it make it that big a difference?
Yes, it's very cool.
Like in the figure, like it.
Right.
Like squaring it brought out that 1 point.
So
is it because i's can be plus or minus 1, but once you square it, it's all the same or something? Or
yeah, that's exactly the problem. Okay. So if you just look at the top guy right here, the top line, if we assume we have BPSK, then we can get rid of the Q term, the quadrature term, right, because Q is 0. But the I term is still there, and it's plus or minus 1. And remember that I has some bandwidth and definitely doesn't look like a delta function. And when we multiply it to cosine, we're just shifting that bandwidth up to the carrier frequency. And so that's why squaring it solves that problem. And we get this cool thing here.
Nice.
I agree. And there's other techniques to solving this problem. There's something called a Costas loop or Costas loop. I have no idea how to pronounce it, but COSTAS. And it uses something that's kind of similar to this, but it's a better way of doing it. It uses a feedback loop, sort of, and is able to get much more precise estimates of the carrier frequency. But this works perfectly fine for this application.
What if you don't get it? So go ahead, Henry.
I had a question about the DC peak.
Yeah.
Why do we get that, and how can it be ignored, or why?
So the DC peak comes from this term right here, right? And that's just because we square a cosine, and squaring a cosine gives you a DC term. The reason it can be ignored is because it's very easy to distinguish between the DC component and the double the frequency component, right? Because we have two distinct peaks. We know the one at 0 hertz is DC. And we know the other one must be the double the carrier frequency. Right?
Yeah.
So yeah, you just ignore the DC and look at the other one.
This all happens like simultaneously, right? Or
Simultaneous to what?
or like, I guess if you go to the previous slide, it like performs all of these operations, like, and it obtains the carrier frequency at once. Like it doesn't like happen through multiple cycles.
Right. So
like, because then you say like, oh, he has to detect this, then get rid of the DC. I don't know. Just I'm thinking of like a series.
Right. So what you do, you know, first you get this, right? This is a given, and that's just you know, directly what you receive from the antenna, essentially, right? I mean, there's of course attenuation and noise, but we're ignoring that for now. And before you demodulate this and obtain your baseband representation of your modulation, you have to know the carrier frequency. So what you do first is you would obtain a packet of information, essentially, which contains some number of symbols. And you would perform this entire algorithm on that packet. So when you're receiving information, you don't go symbol by symbol usually. You always have to obtain a packet first, and then that packet contains, you can perform operations on that packet all at once. You don't have to go symbol by symbol.
Thanks.
Mm-hmm. And then the other thing is, all this math here is assuming that we're not going symbol by symbol, really, right? Because if we did go symbol by symbol, then we'd have a windowed cosine, and the Fourier transform of a windowed cosine is essentially a sinc function. And so by using a longer sequence of symbols, you make that sinc function narrower and narrower, and that gets you a sharper and sharper peak at the double frequency component, which is so similar to what I talked about with the filters, which is having a larger time duration gives you a sharper transitions in the frequency domain. So if you have only a short symbol or a short duration of information, you can't get these sharp peaks here. So you have to use a large number of symbols. I think here I used around like 20 or 50 or something like that, but I forgot the exact number.
So if you want to transmit a very small amount of like a very small sized packet, it would kind of make it hard to use this technique to determine the exact carrier frequency.
Right. But of course, there's other. So if you only have, like, let's say 2 symbols, for example, then what could happen is, your first symbol might show up here, and your next one might show up here. And as long as they're close enough together, basically not enough time has passed for you to start rotating around the entire constellation diagram, then you're okay, right? So like the shorter the duration, the larger frequency offset you can tolerate. Though, I mean, to a certain extent, right? Because if your symbols are too slow, then you start rotating a lot.
If we can differentiate which of the points in the constellation diagram correspond to like the order, which order symbol was received,
Mhm.
can you estimate the frequency that way by like how fast the phase
Yeah. So
grows?
that's exactly another way of doing it. So what you do is usually when you send a packet, the packet has a header, and the header has a known sequence of symbols. And so knowing that sequence on both the transmitter and receiver allows you to estimate a lot of these factors here without doing all this this math here. Though, I mean, they only work to a certain extent. I mean, both methods only work to a certain extent. And I'd argue sometimes using a packet header can be more troublesome in some sense.
Wait, then why are they used all the time though?
Well, you'd use them, but for certain, like in this particular application, knowing the uh, the carrier frequency, you first have, like if you wanted to use the packet header, you first have to detect where the packet header starts in time, because your transmitter is sending packets, your receiver is always listening, but the receiver doesn't know exactly when a packet starts, right? And so you first have to find when the header starts, but if the header is not what you really expect it to be because of the carrier frequency offset, then that can make it a little more difficult detecting where the header starts.
Gotcha.
So I mean, there's a whole series of gotchas with this stuff. Okay, anything else?
Will we talk about how to see when the information starts? Like how do you
Yes.
differentiate like no signal versus signal? You're just always listening.
Yeah, we'll talk about it, not in this lecture, potentially in the assignment, but if not, it'll be next lecture. But you know, a little preview. If you're sending, you know, a known sequence of bits, you know, let's say just something like that, and the receiver knows that this is the start of a packet, then what you can do is you can use a cross correlation of this exact function with what you receive. And when these two line up, you'll get a spike, or you know, a spike in your cross correlation, and that spike denotes where your packet starts. And if you don't know, cross correlation is very similar to a convolution, minus the flipping.
Right. I know what that is. Okay. So wait, so you collect a bunch of data and then you do the cross correlation to then you can figure out which sample is this like true start of that useful information.
Right.
Okay.
So like you kind of think of a cross correlation like this. So let's say, you know, let's say you have two rect functions, and you take the convolution of the two, and the output, right, is a triangle, right? And so the triangle reaches its maximum when these two rect functions line up with each other. And it's a similar idea here. When what you receive lines up with what you expect, you'll have a spike in the cross correlation. right?
Like how often would like a microcontroller check if it's received useful information? How does it,
In general, you have to be listening all the time,
right?
but it really depends on your particular system. So what you could do is just have a running cross correlation where you're basically sliding this function along what you receive, and
Oh, you can do it
continuously do that.
continuously.
Yeah.
Okay, that's right.
Though the actual implementation of that in an MCU can be a little tricky. You have to use DMA and everything, but that's the implementation detail, which we won't go into because we don't have MCUs.
Yeah, I can see how that would work. Okay. Right, I was thinking about you'd have to like collect some amount of information and then stop and then check it, and then
Well,
you said but there's a way to do it continuously. I didn't think about that.
well, that's kind of what you have to do in practice,
No.
because and what you do is you'd use DMA, which means the ADC on your MCU will run continuously. It'll continuously receive information, but you'll process that information in short packets. But you'll still get everything. You'll just process things in packets.
Yeah, I was just imagining that running into the problem of like, what if you split your packet up in just the wrong way, where like you cut the information you're trying to receive in half or something.
Right. Well, that's why you have your packets overlap each other.
I see this is gonna turn into a very long conversation at some point.
Yes, we can discuss.
Okay, cool.
All right. So on to phase offset. So this one is, I think, fairly straightforward. So the simple strategy is you have your two BPSK points. You do a line of best fit that goes through the origin. So kind of like a least squares kind of thing. Yeah, through those points. And then you find the angle of that line with respect to the real axis of the constellation diagram. And if all goes well, you should get the phase offset, or at least a good estimate of the phase offset. And of course, the noise, which is what's creating the cloud of points, will deteriorate that estimate. But assuming you have enough symbols, you'll get a good estimate, right? Because the mean of the noise is 0, so on average, you should get a line that the average estimate you get should be exactly what the phase is. So that's one way of doing it. A better way of doing it, at least for BPSK, if you have more complex modulations, of course, you need more complex methods of doing this. But what you could do is you can take one cloud of points and multiply its phase by -1, which will basically rotate at 180 degrees and bring it to be right on top of the other cloud of points. And then you take the average phase of just this cloud of points, and that'll be that'll be the phase offset, really. I might be forgetting a minus sign here. Yeah, that should be -45. But yeah, that'll get you the phase, and then you multiply every single point by e to the j of that times that phase, and you'll rotate everything back to where it should be. So what we've done is we've gone from frequency offset and phase offset. We've got rid of the frequency offset first, then we get rid of the phase offset, and then we get back to our nice BPSK constellation diagram. Right, any questions on that?
Okay, can you go back one slide? Okay, so here there's one, it could either be 135 degrees out of phase or 45.
Right. Yeah, I was wondering if somebody would pick up on this.
Okay.
There's
So-
ambiguity.
Okay, and would we just assume most of the times that the smaller number is the correct one? Or
No,
is
you
it-
can't make that
there's-
assumption.
Okay, so how do we know, I guess?
So here's
there
where
a
that
way to
packet
know?
header comes in,
Oh,
right?
here we
So
go.
if you're rotated the wrong way, then your bits will be flipped essentially.
Mhm.
And if you make your header in such a way that it's not identical if you flip the bits, then you'll know which way is the right way.
Okay. But you don't like packet headers.
No, no, I don't.
Okay.
I don't not like them. I think they should be used.
Okay. Yeah, that makes sense.
I'm an official supporter of packet headers. Let it be known.
Good to know.
Okay. For example, in 4G LTE communication, the packet headers are fairly integral to the actual working of the entire system. And they provide another application of them is in what's called channel estimation. So if you know exactly what header the transmitter is sending, and you receive the header, and if you take the Fourier transform of that header packet, or the packet header you receive, you can kind of divide what you should be receiving by the Fourier transform of the packet header, and that'll get you the transfer function, or the frequency response, I should say, of the channel. And so then you can do what's called channel equalization, which is kind of canceling out the effects of the channel, like the attenuation and the frequency selectivity of the channel, which might be the case. So some frequencies might be attenuated more than others. And so that'll allow you to estimate those effects and cancel them out. So that's another application of packet headers.
It's kind of cool, man.
It's very cool. I recommend you take 233.
My God.
Okay, so if there's no other questions, we'll move on. Okay. So the last thing we'll talk about in this lecture, at least, is symbol timing, and I won't go into the details here, but basically, if your transmitter clock is, it might be, let's say, 16 megahertz or 168 megahertz or something, and your receiver will have its own clock. Let's say it's 16 megahertz plus 0.001%. So that means when you're receiving data, the effective sample rate of your receiver will be slightly different than the transmitter sample rate. And that'll affect the frequency offset, the carrier frequency offset, but we know how to correct for that. But it'll also affect the symbol rate, how many symbols you're sending per second from the perspective of the receiver. In actual time, it's one precise number, unless you do some like theory of relativity stuff. But from the receiver's perspective, it'll be a little different than what it actually should be. So you need some way of synchronizing that too. And there's a number of ways of doing it. The simpler, or I should say the simplest one, is to use a packet header, of course, which contains symbols. You know exactly which symbols it should contain. And if you know, you can detect where those symbols occur, and that'll give you an estimate of the symbol timing. If you didn't want to do that, then you could look for when your baseband waveform crosses 0. So BPSK goes from 1 to -1. And so when it crosses 0, that's exactly in between two symbols. So you could take two consecutive 0 crossings and determine the symbol timing from that, or a symbol period. You can also do it in the frequency domain using a kind of a similar strategy to the carrier frequency estimation. And yeah, right here, I say more on this in the assignment. So I'll write up an explanation of like how these methods work in the assignment document when I post that. But yeah, that's it for the simple timing at least. So any questions on that?
A simple question. The thing we looked at earlier to estimate the carrier frequency, does it have an official name, or are we just calling it literally carrier frequency estimation?
I don't know of a name. Maybe there is one, but yeah, I don't have one for you.
Okay.
Alrighty. So on to the assignment to be posted tomorrow, Saturday, like I always say, but we'll see if that happens. I'll try and make it happen. So what you'll be doing is mainly modifying the simulation you made in assignment 5, and we'll be adding in all this information we got from this lecture. So you'll first replace those low-pass MATLAB filters that you use in demodulation with your own FIR filters that you'll design. You can use a filter to represent the wireless channel. And so that wireless channel might include frequency selectivity or band limited, meaning it essentially acts like a bandpass filter, or I should say a low pass filter maybe. And so part of your, it'll basically create intersymbol interference, which is the undesirable property that we want to correct for usually using the root raised cosine filters. And so that's the next step, which is you want to calculate the FIR filter taps for the root raised cosine filter. And you'd use that impulse response I listed back a few slides, which you can also find on Wikipedia in case I made a mistake. I hope I didn't. And so those would be applied to both the transmitter and receiver signals to obtain a raised cosine filter overall. Remember, multiply 2 root raised cosine filter frequency responses and you get the raised cosine filter. And then lastly, you'll perform the estimations to correct for all the offsets in your receiver. And so, it's carrier frequency, carrier phase, and the timing and all that stuff. So any last minute questions? No last minute questions. Okay, so we'll call it a day then. Hope you enjoyed your stay.